When we gather all of these individual partial derivatives into a column vector, we get the gradient of the function. The gradient points in the exact direction of the steepest possible ascent on our multidimensional surface, and its magnitude tells us how steep that slope is. To understand why the gradient points in the exact direction of the steepest possible ascent, we examine the relationship between the gradient and the directional derivative. When we calculate the directional derivative of a function in the direction of any arbitrary unit vector u, it is mathematically defined as the dot product of the gradient vector and the unit vector u by the geometric definition of the dot product. This is equal to the magnitude of the gradient vector multiplied by the magnitude of the unit vector multiplied by the cosine of the angle theta between them. Because the unit vector always has a magnitude of 1, the directional derivative simplifies to the magnitude of the gradient vector multiplied by the cosine of the theta. As we move across the surface, the magnitude of the gradient is a fixed value at any given point, which means the only variable that changes the rate of change is the cosine of theta. The cosine function reaches its absolute maximum possible value of 1 when the angle theta is equal to 0 radians. For the angle theta to be 0, the unit vector must point in the exact same direction as the gradient vector. To illustrate this with a concrete example, consider the function f of x and y equals x squared plus y squared at the point 1, 1 dot. The partial derivative with respect to x is 2 times x, and the partial derivative with respect to y is 2 times y, which gives us a gradient vector of 2, 2 at our point. The magnitude of this gradient vector is the square root of 2 squared plus 2 squared, which equals the square root of 8. If we compute the directional derivative in the direction of any unit vector u with components u1 and u2, we get 2 times u1 plus 2 times u2, which equals the square root of 8 times the cosine of theta. To maximize this rate of change, we need the cosine of theta to equal 1, meaning theta must be 0 degrees, which forces our direction vector to align perfectly with the gradient vector 2, 2. Let us consider a second example. Suppose we have the function g of x and y equals 3 times x squared plus 4 times e squared at the point 2, 1 dot. The partial derivative with respect to x is 6 times x, evaluating to 12, and the partial derivative with respect to y is 8 times y, evaluating to 8, giving us a gradient vector of 12, 8. The directional derivative in the direction of a unit vector u is the dot product of 12, 8 and u, which simplifies to the magnitude of the gradient multiplied by the cosine of theta. Once again, because the magnitude of the gradient is fixed at the square root of 12 squared plus 8 squared, which equals the square root of 208, the directional derivative depends entirely on the cosine of the theta. To achieve the steepest possible ascent, we must choose our direction to make the cosine of the theta equal to 1, which requires moving directly parallel to the gradient vector 12, 8. This mathematical necessity proves that the gradient vector always points along the path of maximum increase, because it aligns the direction of movement with the peak of the cosine function. To find the equation of a tangent line or a tangent plane when you are given the gradient vector at a specific point, we use the components of the gradient as the slopes that dictate how the function changes in each coordinate direction. In a multi-dimensional setting, a function of 2 variables defines a curved surface in 3-dimensional space, and the tangent object at any given point is not a single line, but a flat tangent plane. Suppose we have a function f of x and y, and we want to find the tangent plane at a point x is 0, y 0. First, we evaluate the function at our point to find the z-coordinate, or the height of the surface, which we will call z0, defined as f of x 0, y 0. Next, we compute the gradient vector at that point, whose components are the partial derivative with respect to x and the partial derivative with respect to y. These partial derivative values serve directly as the slopes along the x and y-axis. The general equation of the tangent plane is then given by z minus z, 0 equals the partial derivative with respect to x evaluated at our point multiplied by x minus x plus the partial derivative with respect to y evaluated at our point multiplied by y minus y0. Let us illustrate this with a concrete mathematical example. Suppose our function is f of x and y equals x squared plus 3 times y squared, and we want to find the tangent plane at the point 1, 2. First, we find the height by plugging 1 and 2 into our function, giving us 1 squared plus 3 times 2 squared, which equals 1 plus 12, or 13. So our point in three-dimensional space is 1, 2, 13. Next, we find the gradient vector. The partial derivative with respect to x is 2 times x, which evaluates to 2 when x is 1. The partial derivative with respect to y is 6 times y, which evaluates to 12 when y is 2. This gives us a gradient vector of 2, 12. Now we substitute these values into our tangent plane formula. We get z minus 13 equals 2 times the quantity x minus 1 plus 12 times the quantity y minus 2. If we expand and simplify this equation, we distribute the 2 to get 2 times x minus 2 and distribute the 12 to get 12 times I minus 24. Combining all of the constant terms, we get z minus 13 equals 2 times x plus 12 times y minus 26. Adding 13 to both sides gives us our final equation for the tangent plane, which is z equals 2 times x plus 12 times y minus 13. Let us consider a second example to make this even clearer. Suppose we have a function g of x and y equal to 4 times x cubed minus 5 times y squared, and we want to find the tangent plane at the point 2, 1. First, we find the height by evaluating g of 2, 1, which is 4 times 2 cubed minus 5 times 1 squared, yielding 4 times 8 minus 5, or 32 minus 5, which equals 27. Our point is therefore 2, 1, 27. Next, we find the partial derivatives. The partial derivative with respect to x is 12 times x squared, which evaluated at x equals 2 gives 12 times 4, or 48. The partial derivative with respect to y is negative 10 times y, which evaluated at y equals 1 gives negative 10. Thus, our gradient vector at the point is 48, negative 10. We plug these values into the tangent plane equation, resulting in z minus 27 equals 48 times the quantity x minus 2 minus 10 times the quantity y minus 1. Expanding the right side gives 48 times x minus 96 minus 10 times y plus 10. Combining the constants negative 96 and 10 gives negative 86, and adding 27 to both sides gives the final equation for the tangent plane as z equals 48 times x minus 10 times y minus 59. This demonstrates how the components of the gradient vector provide the exact slopes needed to construct a linear approximation of a curved surface at any given point.